Hello. Today I'd like to show you some things about finding factors and prime factorizations and common factors, which will be some basic skills that we'll need as we factor polynomials later on in this polynomials unit. So first thing is just the term factor. What is a factor? What does it mean? A factor of a number is a number that divides that number evenly, that leaves no remainder. So, for example, like 40, 40's got a lot of factors. 40 could be divided by 1. 40 divided by 1 is 40. 40 could be divided by 2. 2 is a factor, because 40 divided by 2 gives us 20. 40 cannot be divided by 3. At least not nicely. It leaves a decimal and a fraction, and so 3 is not considered a factor of 40. And to list all the factors of a number, the most efficient way of doing that, I think, is to just start with 1. Try dividing it by 1, try dividing by 2, by 3, by 4, by 5, and so forth, and just keep going until you've listed all of them, until you see a repeat. So this can be done pretty quickly on a calculator. So if you want to try a bunch of things, I would just do 40 divided by 1, and then 40 divided by 2. And anytime you see a clean pair come up, write them down. 40 divided by 3, no, not going to write that one down. 40 by 4 works. 40 divided by 5 works. 40 divided by 6 does not. Had I been smart, I probably could have not tried that one, but 40 divided by 7 doesn't work, and 40 divided by 8, as soon as I've seen this pair, I've done that one before. I had 5 and 8 earlier. 40 divided by 8 gives me 5. That's really the same combination, and so I can quit at this point. I don't have to keep going all the way up to 40 because I'm not going to find any new pairs. That's the convenience of doing them systematically in order, starting at 1 and 2 and 3 and so on down the line. Now that works great for small numbers like 40, but what if my number was, I don't know, 14,720, and I needed to find all the numbers that divide that? That's going to get pretty tedious to divide and so forth, and I'm already starting to make mistakes here, and try to divide by 3 and so forth. Kind of obnoxious. A nice trick that I've taught my algebra students in years past is to go to the y equals screen. Usually you go here for graphing, and I don't really want to go graphing today. I'd like to take advantage of the table tool. And so if I type, let's go with the example we just did, 40. Remember I divided that over and over and over again by different numbers. If I type 40 divided by a bunch of numbers, so a variable, 40 divided by x, and then if I look at the table, so hit second graph, you will see all those combinations that we just saw earlier. So 1 and 40, 2 and 20, 3 and, well, that one didn't work, 4 and 10, 5 and 8, and the next combination I see here is 8 and 5. I didn't have to type much of anything, and I can see all those combinations here. If I were to scroll down through this list and keep checking, I don't see any other nice pairs except for combinations I've already seen, like 2 and 20, and then the next nice pair is 1 and 40. After that, there's nothing. So that's kind of convenient. If I go back to y equals, what was that weird number? 14,720, I think. Let's try that. 14,720, and divide by x. And now look at the table. And I can scroll through this list and just pick out the numbers that match. Or not that match, that are nice numbers. 1 and 14,720, 2 and 73060, and so forth. I'll skip 3 because 3 did not divide cleanly. And I can scroll through this list. I will know that I have reached the end of the list when I either see a pair that I've already seen before, or so far all of the x's have been smaller than the y's. As I keep going, eventually the x's will be bigger than the y's. Getting close. And that's another time when I could stop. At this point, I'm not going to see any other new pairs now that the x's are bigger than y. The next pair that I see, 128 and 115, I actually already saw earlier, 115 and 128. So there's one way, one thing that you can do to list all of the factors of a number. Why would we do it? I don't know. Sometimes it's nice to know what things are divisible by, but typically that skill is not something that's crucial for anything else. So now, another related idea to listing all the factors is to consider just the factors of a number that are prime. They're kind of unique things. Prime numbers are numbers that don't have any factors except for 1 and itself. So the numbers here, 2, 3, 5, 7, 11, 13, 17, 19, 101 is an example of a prime number. Those are all numbers that can't be divided by anything except for 1 and themselves. And so one thing that's often done is to take a number and write it in a way that is just multiplying by prime numbers. And when you do this, you get a unique kind of fingerprint for a number. So technically, a prime factorization is the unique way of writing how to produce a number by multiplying only prime numbers. So here's a few examples. 24, for instance, its prime factorization is 2 times 2 times 2 times 3. That's the only way that you can write it that is multiplying only prime numbers. And every number has its kind of unique fingerprint like this. So now, how can we find prime factorizations? I have learned kind of two techniques for finding prime factorizations. One, I've heard called upside down division, or sometimes I've heard it called the ladder method, because it kind of looks like a ladder when you do it. And then another technique is called a factorization tree. I personally prefer factorization trees, but I won't let my bias affect you. I'll show you them both, and you can choose for yourself which one you like better. So, to find the prime factorization of 300, using the upside down division method, that would mean start by trying 300, and let's divide it by the lowest prime number, 2, as many times as we can. And so 300 can be divided by 2, and that gives me 150. And then 150 is also even, so that can be divided by 2, and that gives us 75. 75 cannot be divided by 2, and so the next thing we'll do is we'll try the next highest prime, and that is 3. 75 can be divided by 3, and so 75 divided by 3 is 25. And 25 cannot be divided by 3 anymore, so we'll try the next highest prime number. After 2 and 3, then there's 5. So 25 can be divided by 5, and that gives us 5. And 5 can be divided by 5, and that gives us 1. And when we get to 1, we are done. And this combination of numbers, 2 times 2 times 3 times 5 times 5, is the prime factorization. 2 times 2 times 3 times 5 times 5. It's the only way of writing 300 as a multiplication of only prime numbers. Sometimes people will write it with powers. So 2 squared times 3 times 5 squared. That's okay too if you want. So, now, the other way of finding prime factorization is to use what's called a factorization tree. And to do a factorization tree, I like to start with the number 240. And I will think of any combination that I can possibly think of that multiplies up to 240. Doesn't matter what you see. The first thing that comes to mind. So I saw the 0 here, and so that meant I knew it was divisible by 10. So 24 times 10 is the same thing. So I'm going to write 24 times 10. Now, 24, what's the first thing that you think of that multiplies up to 24? For some, it's 2 times 12. For others, it's 3 times 8, maybe 4 times 6. It doesn't matter. Pick one and write it. I saw 4 times 6 first of all. So I'm going to write 4 times 6. 4. That's 2 times 2. And 2 is a prime number. It can't be broken down anymore except for 1 times 2. It's the only way to do it. So once you get to a prime number, circle it. And then here, that's also a prime number, so I'll circle it. 6, I think is 2 times 3. And those are both prime numbers. And then 10 is 2 times 5. And so that's 2 and times 5. And those are both prime numbers. And so I circle that. And as soon as you have only circles, then we are done. And we just list these factors in order. So 2 times 2 times 2 times 2 times 3 times 5. That's 2 to the 4th times 3 times 5. So that's finding the prime factorization using a factorization tree. The reason I like this method better is because it's a little more flexible. It doesn't matter what numbers you choose. I chose 24 and 10, but let's suppose I did instead 2 times 120. Maybe that's the first combination I saw. Then 2 is prime, and 120 can be broken down. Maybe you see that that's 2 times 60. And then 60, I remember, is 6 times 10. And 6 is 2 times 3. And 10 is 2 times 5. And so all those prime factors, guess what? It's the exact same combination of numbers. I still get 2 to the 4th times 3 times 5. And no matter how you break down 240, it always gets you the same thing. And I just kind of think that's magical. I like that. I think it's cool. And so that's why the factorization tree happens to be my favorite. It can also be kind of useful for a number like, I don't know, maybe 3,000. If I wanted to break that down, I don't have to do it in branches of 2. I could do this as 3 times 1,000, and I know that 1,000 is 10 times 10 times 10. And then 10 is 2 and 5, and 2 and 5, and 2 and 5, and so forth. And so if you see combinations like this, that can kind of shorten your work a little bit, and so forth. So that's why I like the factorization tree. It really doesn't matter. Both methods work and work well.